Assalamualaikum and hi, we are from Group 3. We'll be presenting about the experiment minor losses in pipe. So this is our team members, SYAFIQAH, NAJLAA and LAKSHMI. First one is introduction. So energy losses in pipe are caused by friction and are divided into major and minor losses. Minor losses can happen due to pipe fittings, changes in flow path and variations in pipe size influenced by factors like fluid velocity, pipe diameter, flow direction and pipe length. This experiment aims to measure the loss coefficient KL and head loss HLM in pipes for different water flow rates, pipe diameters and bend types. The second one is the objective and scopes. So the objective is to determine the loss coefficient and minor head losses for different water flow rate, pipe diameters and pipe bends. And then the scope, the study consists of different pipe components which are sudden enlargement, sudden contraction, pipe branches which are Y-type and T-type, and pipe bends, angle 90 degree, bend 90 degree and angle 45 degree. The study also focuses on collecting volume of 2 liters of water.
The flow in piping system at different flow rates may be required to pass through a variety of fittings, bends, or abrupt changes in area. By simplifying the Bernoulli equation, we can determine total head loss. So, how do we simplify? First, we will remove unwanted variables. Since we do not have pump to add energy and turbine to extract energy, HA and HE will be equals to 0. Since we are investigating a horizontal pipe, there is no height difference. Thus, Z1 equals to Z2. Finally, we have head losses, which can be divided into 2 categories, major head loss and minor head loss. Since we are using short length of pipe, we ignore the major losses and we are left with minor head loss. By rearranging the equations, we will get these specific equations as listed here. The value of loss coefficient is strongly dependent on the geometry of the component considered as well as the fluid properties, which is Reynolds number. In many practical applications, the Reynolds number is large enough so that the flow through the component is dominated by inertia effects, leaving the viscous effect as secondary importance. In a flow which is dominated by inertia effects, it is usually found that pressure drops and head losses correlate directly with the dynamic pressure. Therefore, the friction factor for every large Reynolds number in fully developed pipe flow is independent of the Reynolds number. The same condition is found to be true for flow through pipe components and fittings. Thus, in most practical cases, the loss coefficient for components are a function of geometry only. In this experiment, the loss coefficient value and minor head losses in pipes for different water flow rate, pipe diameter, and pipe bends will be determined. The diagram shows loss coefficient for flow through sudden area changes. The value of loss coefficient for the fluid flows through a sudden expansion and contraction can be obtained by considering the continuity, momentum, and energy equations between point 1 and point 2 for the controlled volume. Those equations can be rearranged to give the theoretical loss coefficient for sudden expansion and contraction as shown here. The figure shows typical values for loss coefficient for pipe components. At the end of this experiment, we are expecting results which has higher flow rate for higher loss coefficients, larger diameter and sharper bends for smaller loss coefficient. As shown in the diagram, the experiment was conducted in the pipe test branch with 7 different fittings. Next, we start to conduct the experiment by opening valve 1 and valve 11 to the maximum. All the switches and pump are switched on, water will start to flow. All the 2 tube manometer are connected and their reading are recorded. Knife valve is closed to collect water. 2 tube manometer are connected and after collecting water, we open back the knife valve to measure the time needed to collect 2 liters of water. The experiment is repeated 4 more times by progressively reducing valve 11. After that, we take out the manometer tube to test another component. Inlet valve for next route is open and valve that are not used closed. The experiment was repeated again, but this time with different component. Once finished, all the switches are closed.
So these are the results obtained from our experiment. For table number 1 is for the data for sudden enlargement and sudden contraction. We're keeping the volume of water collected constant at 2, and then we're finding the time and the QX. QX is basically the volume of the water or over the time taken. And then we calculate the H1 observed and H2, finding the difference of H. Okay, for the second table is the data for pipe branches using the same volume of water collected, which is constant 2, and then finding the QX. And then recording the H1 and H2 and finding the delta H. The last table is the table 9.3, which is the data for elbow and pipe bends, still keeping the volume of the water collected at constant 2, and then measuring the time, calculating the QX, which is the volume of water collected over the time, and then recording the H1 and H2, and then we're going to find the delta H. So these are our results. So here are the discussions that we come up with. The first question in the discussion asks us to calculate the minor head loss HLM and the loss coefficient of KL value for the different components and fitting. For the first calculation is the sudden enlargement. We are given the outer diameter, the thickness, and the length of the tested pipe section. Using that formula, we're going to calculate the upstream diameter first, which is the inner diameter, and then we're going to calculate the downstream diameter. And then we're calculating the area for the cross-sectional of the upstream and the downstream to be used in the table data using a formula. For the kinematic viscosity, we're using the interpolation method because we've been given constant temperature, which is 36 degrees Celsius. And then we're doing the table. We're filling up the table. Q are explained above that we calculated from the result that we obtained. And then we're using the area for calculating the loss coefficient, which we got 0.4117. After filling up the table with the formula stated, we calculate the average minor head loss, HLM, the loss coefficient KL, and the average coefficient of friction, F. And then the second one is for the sudden contraction. The data that has been given is the outer diameter, the thickness, and the length of the tested pipe section. As stated from the first one, we have to find the cross-sectional area of the upstream, the cross-sectional area of the downstream with that formula, and finding the loss coefficient. And then we still have to do interpolation to calculate the kinematic viscosity to be used in the table stated here. The difference between 1 and 2 is the formula for HLM. Specifically for this one, the formula is V2 minus V1. The third one is finding for Y type of branch. We were given the outer diameter, the thickness, the length of the tested pipe section. And then using the same formula to find the inner diameter of the pipes, which is we got 0.0170 meter. Still doing the interpolation to get the kinematic viscosity using the same formula. And then the loss coefficient KL, we got from a table. It is a constant table that will be shown in the fourth working. And then we're going to fill up this table. The Q, as stated earlier, we calculated Q at the results. And then what's changing before and this one is the HLM formula, which is the formula for this one is KL V square over 2G. And then we're finding the average minor head loss, HLM, the loss coefficient, and the average coefficient of friction, F. The working for the T-type branch is basically the same as the third one, but what's changing is just only the data result obtained.
For 90-degree angle bands, we calculated the internal diameter by subtracting the outer diameter with the thickness, and then we calculated the kinematic viscosity to get the Reynolds number. We calculated cross-sectional area, A, and we got the value for KL value from the table, which is 1.5, but since it has two 90-degree angle band, so we multiply it by 2. Since we have the kinematic viscosity and the velocity, we can calculate the Reynolds number to be used to calculate the coefficient of friction, which is F. For 90-degree band, we also calculated the internal diameter, cross-sectional area, the kinematic viscosity to be used to calculate the Reynolds number. So by Reynolds number, we can get the value of F using the formula given. Lastly, for the 45-degree angle, we also did the same step to obtain the value of F. Second discussion asks us to discuss the effects of different water flow rates, pipe diameter, and pipe bands on the loss coefficient, which is KL value. So the loss coefficient, KL, measure energy loss in a pipe. So the first factor that affects KL value, the first one is flow rates. So higher flow rates make the water move faster, causing more turbulent and friction losses. When water moves very fast, the flow can change from smooth, which is laminar, to turbulent, which increases energy losses and raises the KL value because of the swirling motion of the water. The second one is pipe diameter, which affects the KL value. In pipe, sudden enlargement has the highest KL value compared to sudden contraction, as shown in the table, because when water flows into a larger pipe, it spreads out quickly, creating turbulent and energy loss. In sudden contraction, water speed increase, pressure rise, and the flow stay close to the pipe wall, reducing turbulence and making flow smoother. The third one is pipe bands. So 90-degree elbow has highest KL value, followed by band 90-degree and 45-degree elbow. Sharper bands increase the KL value. For bands, the sharper the angle, the higher the KL value. A 90-degree elbow creates the most turbulence due to the direction change, while 45-degree elbow has lower turbulence and energy loss. For Y-type and T-type, they both shown with the same KL value, but in reality, T-type has a slightly higher KL value because it has sharper bands, while Y-type is smoother.
For the third question in discussion, it has to briefly discuss on factors contributing to errors or inaccuracy in experimental data and the possible recommendations to improve the existing results. So, we come up with 3 factors that might be affecting our data, which is the first one is the presence of air bubbles within the tubes and pipes. The second one is unstable water flow rate causing significant fluctuations in the water level between the tubes and making calibration difficult. The third one is the parallax error occurs while reading the meniscus level of water volume and the readings of the manometer. So we also come up with 3 possible recommendations that might overcome the factors that affect our data, which is the first one is to flush the system thoroughly. before used to remove any trap air to avoid air bubbles. And the second one, a larger reservoir can help maintain a more consistent water pressure and flow rate. And the last one is to ensure that readings are taken at the eye level with the meniscus to avoid parallax error. From this experiment, we can say that the loss coefficient KL and the minor head loss HLM is influenced by three types of things, which is the pipe fitting, the diameter, and the liquid flow rate. Sudden enlargement has higher KL and minor head loss value compared to the sudden contraction. The 45 degrees band have lower KL and minor head loss value followed by the 90-degree angle and then the 90-degree turn. While the type branch has the same loss coefficient with the Y-type of branch, but it has higher minor head loss compared to Y-type branch. Specifically, it was observed that the higher the flow rates, the higher the loss coefficient and the minor losses. And the second thing that we come up with is the larger the pipe diameter, the lower the loss coefficient and minor losses inside of the pipe. And then the higher the angle of bending, the higher the loss coefficient and the minor losses. This insight and findings for the experiment effectively contribute to achieving our objective. So here are the safety procedures that we have to consider while doing the experiment. The first one is do not touch the vent and drain valve if there are no bubbles or if the manometer is full. The second one is do not touch the manometer glass to avoid air bubbles. And the third one is to make sure that the eyes are perpendicular to the thermometer reading scale to get accurate results. Okay, so lastly, these listed are all the references that we're using for the experiment to calculate the data and for the theory and the discussions. Thank you.